Hi everyone, today we are going to study chromatic numbers in graph theory. Painting all the vertices of a graph with colors such that no two adjacent vertices have the same color is called proper coloring or simply coloring of a graph. So basically chromatic number is the coloring of the vertices of the graph in such a manner that no two adjacent vertices have the same color. This means that any two vertices can have the same color if they are not adjacent. So colors can be repeated for vertices, but the only thing that we have to take care of is that the adjacent vertices should not have the same color. A graph in which every vertex has been assigned a color according to a proper coloring is called a properly colored graph. So basically this technique of assigning unique colors to assigning colors to every vertex is called proper coloring, and such a graph in which a proper coloring has been done, that means every vertex has been assigned a color according to the proper coloring, is called a properly colored graph. So basically what is proper coloring? That no two adjacent vertices have the same color and you have to assign color to all the vertices of the graph, keeping in mind that adjacent vertices will not have the same color but non-adjacent vertices can have the same color. So this is proper coloring, and when we use proper coloring for a graph, then that graph is called a properly colored graph. Usually, a given graph can be properly colored in many different ways. So there is no such thumb rule for coloring a graph. The only condition that I told you in the beginning is that adjacent vertices need to have different colors. Other than that, there is no such hard and fast rule for coloring a graph. So that is the reason that one single graph can be colored in many different ways. Now let's see an example of that. See, if you look at this figure, so you can see that the figure below shows three different proper colorings of a graph. Same graph has been given proper coloring in three different ways, right? So the one way of providing a proper coloring to this graph is that, now first of all you have to see how many vertices are there in this graph. If you consider this graph, there are total 5 vertices, V1, V2, V3, V4 and V5. V1 has been assigned color red. Now V2 is the vertex which is adjacent to V1. So hence V2 cannot be assigned color red. V2 is assigned color blue. Then V3 is a vertex which is adjacent to V2. So V3 cannot be assigned blue. V3 has been assigned green. Then V5 is also a vertex which is adjacent to V2. So V5 can also not be assigned blue. So V5 is assigned yellow. Then we are left with vertex V4. Vertex V4 is adjacent to vertex V3 and V5. So we have to take care of the fact that V4 should not be assigned a color of vertex V3 or vertex V5. So V4 has been assigned a color pink. So here in this case you can see all the vertices have been assigned different colors. No color has been repeated for any of the vertex. So this is one way of coloring the graph by proper coloring method. So this is one way. Okay, now the another way, if we see, again starting from vertex V1, we have again given it color red. Then vertex V2, because it is adjacent to vertex V1, we cannot assign it color red, other than we can assign it any other color. So here also we have given color blue to vertex V2. Then vertex V3 is adjacent to vertex V2 and vertex V5 is also adjacent to vertex V2. Right? So that means V3 and V5 cannot have the same color as vertex V2. V3 here has been assigned color green. V5 here has been assigned color yellow. Now vertex V4 is adjacent to vertex V3 and V5. That means we cannot assign color green or yellow to vertex V4. But other than that, we can repeat any of these colors. So here we have repeated a color. In this graph, if you see, no color was repeated, but here for V4 we have repeated the color red, because the only condition is that adjacent vertices should not have the same color. So V1 and V4 are not adjacent, so we can assign color red to it. Even V2, but so V2 and V4 are adjacent, so we cannot assign the same color as V2. Similarly, V3 and V4 are adjacent, we cannot assign the same color as V3. V5 and V4 are adjacent, so we cannot assign the same color as V5. So V4 is non-adjacent with only one vertex, which is V1, so we can repeat the color then. Right? So this is another way of doing the proper coloring of graph. Now let's look at the third way. Same graph, same vertices. Vertex V1 again has been assigned color red. Vertex V2 has been assigned color blue, which is different from red for the very reason that V1 and V2 are adjacent, and no two adjacent vertices can be assigned the same color according to proper coloring. Okay, fine. Now next, moving on to vertex V3 and V5. Now V3 and V5 are adjacent to V2, hence both V3 and V5 cannot have the same color as V2. But V3 and V5 are not adjacent, so they can have the same color. So we cannot assign V3 or V5 color blue. Other than that, we can assign it any other color. So we have given vertex V3 yellow, and V5 can also be given the same color yellow, because V3 and V5 are non-adjacent vertices. Now moving on to vertex V4. Vertex V4 is adjacent with vertex V3, vertex V5 and vertex V2. That means you cannot assign the color yellow or blue to vertex V4, but V4 is non-adjacent with V1, so we can definitely allot or assign the same color red to vertex V4 also. So these are the different ways in which you can color a graph, and the only condition is that adjacent vertices should not have the same color. Other than that, if you want, you can repeat the colors for all non-adjacent vertices, or if you want, you can assign unique colors to every different vertex. So this is proper coloring of a graph. Such a way of assigning colors to a graph wherein no two adjacent vertices have the same color is called the proper coloring of a graph, and this can be done in many different ways. We have just seen 3 different ways of assigning color to a same graph. Now a graph G that requires k different colors for its proper coloring and no less is called a k chromatic graph, right? And the number k is called the chromatic number of G. So basically, while coloring a graph, we need certain number of colors. So the minimum number of colors that is required to color a graph, and no less than that, is called the k chromatic graph. Like here we have used as many colors as we could, but these are not the minimum number of colors required. We can do without pink, we can do without pink color over here, but we have used pink color over here. So that is not the minimum number of colors required. That is as much as we wanted. But there is a restriction on the minimum number of colors that would be required, Without that, you cannot color the graph. Like 3 is the minimum number. No less than 3 colors can be used to do proper coloring of a graph. So that means if a graph requires k different colors for its proper coloring and no less than that, then it is called a k chromatic graph, right? And this number k, which can be 1, 2, 3, depending upon the number of colors you have used for the proper coloring of the graph, is called the chromatic number of G. Right? So any such graph is called a k chromatic graph, and the minimum number of colors that were required to do the proper coloring of the graph, keeping in mind the condition that no two adjacent vertices have the same color, then in that case, that k is called the chromatic number, which could be 2, 3, 4, 5, depending upon the graph. So if you look at this particular graph, it is 3 chromatic. Why? Because the minimum numbers of colors that are required are 3. One color is red, second color is blue, and third color is yellow. So 3 is the minimum number of colors that is required for the proper coloring of this graph, and no less than 3. You cannot do without in less than 3 colors, right? Because this vertex cannot have the same color as these two vertices and this particular vertex, right? These two vertices cannot have the same color as this vertex. So using your seeing all the probabilities of different ways of coloring this graph, we found that 3 is the minimum number of colors that are required to do proper coloring of this graph. You can use more than 3, that there is no restriction on that, but minimum you need 3 colors so that the graph is properly colored. That means no two adjacent vertices have the same color. So that means, otherwise you can say, oh, here 1, 2, 3, 4, 5 colors are used, but that is not the minimum number of colors that are required to do proper coloring. That is out of choice. But the minimum number of colors that are required to do the proper coloring is 3 here and no less than 3. It can be more than 3, but it cannot be less than 3, because here you saw the numbers used to do the colors used to do the proper coloring of this graph were 5 different colors. So it can be more than 3, but we cannot do in less than 3. So this 3 is so that is why this graph would be called K chromatic. K here is 3. So this graph would be called 3 chromatic graph, because minimum 3 colors, 3 different colors are used to do the proper coloring of this graph, and no less than 3. You can try it for yourself. You cannot do with less than 3 colors to do the proper coloring of this graph, or else it would not be the proper coloring, because in that case the adjacent vertices would also have the same color, and we cannot do that in case of proper coloring. So the only condition for any proper coloring of a graph is that no two adjacent vertices can have the same color. So keeping in mind this condition, 3 is the minimum number of required colors to do the proper coloring of this graph. As this graph is a 3 chromatic graph, and since there are minimum 3 colors required for the proper coloring of the graph, so the chromatic number of this graph is 3. That is your K equals to 3 for this graph, right? So that is why I said that the graph in the figure above is K chromatic. Now in coloring a graph, there is no point in considering disconnected graphs, right? Because disconnected graphs has different components. So that is why we don't consider disconnected graphs. How we color vertices in one component of a disconnected graph has no effect on the coloring of other components, because different components, that means there would be no adjacent vertices. No two separate components would have adjacent vertices. So that means different components, it does not matter what coloring scheme you have used for one component of the graph to the other component. So how you color vertices in one component of a disconnected graph has completely no effect on the coloring of the other components. Other than that, all parallel edges between two vertices can be replaced by a single edge. While doing the proper coloring, if you have parallel edges in a graph, then what you can do, you can replace the parallel edges by a single edge without affecting the adjacency of vertices. So this would not affect in any case the adjacency of the vertices, because those two vertices would still remain adjacent to each other. For example, if you have say for example two vertices V1 and V2. Now you have parallel edges A and B, right? Because these two edges are incident upon the same pair of vertices, hence A and B can be called parallel edges. Now V1 and V2 are adjacent to each other right now. If I replace these two edges with a single edge like this, V1 and V2 are still there, and I replace these two parallel edges AB by a single edge called AB now. Earlier it was separate edge A and separate edge B. Now I have replaced these two parallel edges by a single edge called AB. So this has not affected the adjacency of vertices. V1 and V2 are still adjacent to each other, right? So that means this would not affect the proper coloring of the graph. So while you are doing proper coloring of the graph, you can replace the parallel edges by a single edge, and this would not affect the adjacency of the vertices. As far as self loops are concerned, they must be disregarded while doing the proper coloring of a graph. Thus, for coloring problems, what kind of graphs need to be considered? We need to consider only simple connected graphs with no parallel edges and no self loops. As far as parallel edges are concerned, you can convert them into a single edge, and the self loops can be disregarded. So the coloring problem considers only simple connected graph. So this is all about your chromatic numbers and proper coloring of the graphs.